We're going to get started this afternoon. We're talking about fault friction, and one reason we're spending the entire session sort of like we spent the entire session talking about gravity and initial stresses is that with fault friction there's a fair number of both numerical and sort of setup complications that make it a little trickier than just running prescribed slip. Concepts covered, we're going to talk about, we call this fault friction. It's often called spontaneous fault rupture. Some people call it dynamic fault rupture, but then they think dynamic versus quasi-static. So some people, we call it within the PyLith code itself, it's dynamic versus kinematic. But people sometimes get confused with dynamic versus quasi-static versus static. So sort of the more generic sort of term would be spontaneous fault rupture. We'll cover quasi-static and dynamic simulations. I'm going to cover static friction, slip weakening friction, and rate and state friction. We now bring in nonlinear solvers even more so than with finite strain. In the dynamic simulation, which we haven't really talked about yet at this meeting, these have wave propagation, and so we put absorbing boundaries. We have time-dependent Dirichlet boundary conditions. So on a lot of the simulations we've been talking about, we've just had roller boundary conditions. Now we're going to increase and drive stresses on the fault. We're going to move the boundaries corresponding to shear. And then also another way to drive the shear stresses on the fault into failure is to actually prescribe perturbations in the fault stress directly on the fault surface, and that's what we generally use in dynamic simulations. I'm going to spend a little bit of time talking about the fault friction interface and implementation. So here's our generic diagram of some domain with the fault surface and our relative displacements and tractions. Recall that we have a normal vector on the fault. The normal vector points towards what we call the positive side of the fault. And then there's the opposite side is the negative side of the fault. And yesterday I showed how in terms of the fault implementation, in terms of the tractions and balance of stresses, much like we have for the Neumann boundary condition on the fault surface, on the positive side of the fault, we have essentially a negative Lagrange multiplier traction, and on the negative side of the fault we have a traction equal to the Lagrange multiplier, and then we have our constraint relationship with the slip minus relative displacement equaling 0. For our fault constitutive model in PyLith, the shear components of the Lagrange multiplier, their values correspond to the tractions on the fault. So if we have a friction criteria, the Lagrange multipliers in the shear direction must be less than or equal to the tractions allowed by the friction model. And the friction model is generally of this form. When the normal stresses are less than 0, so the fault surface is touching compressive tractions, we have that there is a cohesion traction minus the coefficient of friction times the normal traction. So with a normal traction less than 0, this is a positive contribution, as well as the cohesion is generally positive. When the fault is, the friction model says that, well, as the normal stress goes to 0, you have just the cohesion term. Now we also have another sort of secondary condition that the normal the traction normal times the displacement normal is equal to 0. And so when we have compression, we have no interpenetration. So when the left-hand side, T normal is less than or equal to 0, then U normal must be equal to 0. So this is the slip in the normal direction is equal to 0. I should have put slip here instead of just the displacement. But then if I have opening or a tensile on the surface, then I want the slip is you're going to separate the two sides of the fault. So the slip essentially is positive, that means the normal stress is going to 0. And so generally we set, once you have opening, if you have tension on the fault, such as if you pull apart the fault associated with a dike, then we set the tractions on the fault surface to 0. And here is the algorithm we use to solve and update the equations based on the friction model. So first, we perform a nonlinear iteration, assuming that there's no additional slip at the time step. Then we check to see if the fault constitutive model is satisfied. If the fault constitutive model is satisfied, then at that time step, there's no additional slip. So basically, we're back in sort of a locked fault condition or a sticking condition. If it's not satisfied, what we do, because we have the Lagrange multipliers as an unknown and generally the slip on the right-hand side, we want to estimate the slip required to reduce the traction down so that it is consistent with the fault constitutive model. So basically, first, if we have say we're driving the shear stresses by deforming the domain, so we're increasing the shear stress on the fault, at some point we realize that, okay, the fault needs to slip. Then the question is, because the shear stress is above the allowed shear stress by the friction model. So we're going to bring our Lagrange multiplier down so that it is equal to the amount allowed by the friction model. And to do that, we need to increase the slip. So we want to estimate how much slip is needed to make so that the fault constitutive model holds. So here I have extracted the portions of the equations consistent with our stiffness matrix times displacements on the positive side of the fault, our Lagrange multipliers for the positive side of the fault, the displacements, and then our sort of force term for the positive side of the fault. The next line is for the negative side of the fault, and then the bottom line is the equations for those Lagrange multipliers. Sorry, these aren't the Lagrange multipliers, these are basically direction cosines associated with the orientation of the fault. So this is basically K times U plus, and before I've labeled this C times the Lagrange multiplier is equal to B. Now then, we want to find out the perturbation in the Lagrange multipliers to satisfy friction. Basically, we want to solve for the Lagrange multiplier so that, we have a perturbation in the Lagrange multiplier and we want to solve for how much slip we have. So here we take this term times the perturbation in the displacement field and then move this term times the perturbation in the Lagrange multipliers to the right-hand side and set these equal to 0 because we're doing a perturbation where these aren't changing. So we have these two set of equations that tell us for a change in the Lagrange multipliers, what does the displacement do? If you subtract these two equations, you'll see that you end up with that equals the slip on the fault. So this is a small subset of the entire system where we're looking at the perturbations in the Lagrange multipliers to satisfy our friction criteria and determining what the displacement field looks like for that to be true. And then we can update our slip and then do another iteration of the nonlinear solve. This is a little bit complicated. Our new formulation that'll be coming out soon eliminates this perturbation, but right now this is what is in PyLith. So that's just explaining. I didn't write down what the change in the equations is, but basically we're going to make improvements in the future. So some words about friction and the nonlinear solve parameters. Because we're using iterative solutions, the fault will not be, even with we want the fault to basically not slip, even though the displacements might be 10 to the minus 10, or 10 to the minus 11, or 10 to the minus 8. So there is a zero tolerance parameter for the fault that defines at what threshold is the relative displacement across the fault. Should we really consider it to be locked? And so that's what this zero tolerance parameter for the fault is. Then we also have the solver tolerances for PETC. And because the nonlinear solve has the internal sort of linear solve. We want the linear solve to be less than the zero tolerance. If you have a tolerance that's above the zero tolerance, PyLith will never think the fault is locked because the solver will stop driving down the residual, and you'll have, it'll think, oh, well, this is, you told me I only needed to solve to an accuracy of like reducing the residual down to like 10 to the minus 7. But if you say the round off errors that I accept to between a locked fault and a sliding fault is 10 to the minus 12, PyLith won't think that the fault is locked. It'll think, oh, even that displacement of 10 to the minus 9 is something that you're trying to resolve with slip. So you need to pay attention to the zero tolerance as well as the relative tolerance and absolute tolerances of the solver. Now the nonlinear solver generally should be a little above what the locked or the zero tolerance is. So here's an example of what we typically do is we put a zero tolerance, and this is an absolute tolerance of 10 to the minus 11. You can bump all these values up or down 1 or 2 orders of magnitude. We do our linear solver tolerances. We don't want, because the zero tolerance is an absolute tolerance, we need to drive the linear solver to converge in an absolute sense. So we'll put an order of magnitude less on the linear solver absolute tolerance, and then a very, very small relative tolerance so that the linear solve will never be satisfied by the relative tolerance convergence. It's a solved, it'll stop iterating with the absolute tolerance convergence. For the nonlinear solve, we do the same thing for the relative tolerance, but then we back off the absolute tolerance. So the nonlinear solve should always have a less stringent criteria than the linear solve and the zero tolerance in between. And that inner solve also can have its own preconditioner, and so here are the settings that we often use in our friction problems. And right now, PyLith does not check what these tolerances are to verify that the SNES is bigger than 0, that is bigger than the KSP tolerance. So it's up to you to ensure that those are correct. But if these get off, then it's pretty clear usually either the nonlinear solve doesn't converge, or when you look at the output, you'll see weird things going on in the fault. You'll see basically it looks like noise. You'll see parts of the fault moving that shouldn't be moving, and that's usually an indication that the linear solve is failing to converge. So fault constitutive models, PyLith has static friction, slip weakening friction, time weakening, where we replace slip in the slip weakening model with time, and rate state friction. There are also some additional less popular fault constitutive models within PyLith that were used in some specific benchmarks that generally there's no real physical meaning. They were done there, created basically for artificial numerical characteristics associated with some specific benchmarks. So static friction, coefficient of friction is equal to some value. Slip continues. An important thing to notice here is that as you continue to drive your stresses, slip will continue once you've reached that shear traction. You can never get stick-slip behavior with just a constant coefficient of friction. And so generally this is only going to be useful if you have a static simulation. Now with slip weakening, the slip will decrease linearly as slip increases till it reaches some threshold, and then the coefficient of friction will remain constant. So we definitely refer to this as a static coefficient of friction here where there's zero slip, and a dynamic coefficient of friction out here. And then there's a linear transition as slip increases from 0 to D0. Now this will generate stick-slip behavior, and once the fault has locked again, it resets itself back to the original static coefficient of friction. And if I remember correctly, I believe there's a parameter where you can turn this resetting on and off. Time weakening, we replace slip on the horizontal axis with time. And this is generally more numerically stable in dynamic simulations because you control how fast this weakening occurs. but there's no physical mechanism associated with this. There is thought to believe some physical mechanism associated with this transition from static sliding to dynamic sliding over some distance of slip or length scale of slip. Rate state friction, here I'm showing the coefficient of friction as a function of log of the slip rate. So this is a slight variation of the familiar form. If you ignore this second term on the lower right, it looks like normal rate state friction. The difficulty with rate state friction is that as the slip rate approaches zero, the friction tends to just keep, well, you can, this, the first equation here is not defined if the slip rate is zero. So if we ever have a locked fault, even as we drive the slip rate down to 10 to the minus 30, which we can't sort of resolve with our iterative solver, the fault would never lock. And so what we did in our implementation is that once you reach some basically linear slip rate, so V linear, once you reach that threshold, then the coefficient of friction becomes constant. So V above V linear, you use the normal rate and state friction. Below that, it's basically in log space a constant coefficient of friction at lower slip rates. This provides some stability, but also gives us a nice smooth transition between the two, where this line here would correspond to sort of keeping the top equation as a function of log. And the evolution law here is theta is related to sort of the time scale, and this is slip rate over some length scale. So the main additional components that are involved with when you do a simulation with fault friction, you have a fault cohesive din. So this is dynamic as compared to the kinematic. You have a friction model. Traction perturbation, you can, in some cases, you'll leave this out if you're driving it from far field deformation, and then the nonlinear solver. Here's a description of what those parameters look like in a .cfg file. So first we change the type of faults. Then for our friction model, we specify what type of friction we want. Usually there's a spatial database associated with it. We also usually give a label for that friction model. And so here we're going to use a uniform database for static friction. There's two parameters for the friction model, the friction coefficient and the cohesion. In this case, the friction coefficient is 0.6, and then given a value of 0 pascals for the cohesion. An example of a traction perturbation is shown at the bottom. So here I used a simple spatial database, put in a spatial database / tractions.spatialdb. And this is most often used in a dynamic rupture where you want to nucleate a rupture at a specific point. So you know where the hypocenter of the earthquake should be. So at some location you slowly increase the tractions above the threshold and expand that area over which those tractions increase until the rupture will spontaneously start propagating on its own. So now let's look at some simulations for static friction and then quasi-static friction. These are examples 3D hex 8, and we'll start at step 10. This is just static friction. Here we'll be moving we'll push the boundaries of the box closer together, and then we'll put on shear, and it won't be enough shear to cause the fault to slip.